Welcome once again. My name is Jan Börner. I'm one of the two speakers of the Transdisciplinary Research Area's Sustainable Future at the University of Bonn. I'm here to introduce our speaker for today. We are happy to have invited Professor Hannah Cloke. She's a physical geographer, a natural hazards researcher, climate scientist, and hydrologist who specializes in Earth system modeling and also flood forecasting, catchment hydrology, and applications of numerical weather predictions, but also science communication. She's a co-director of the Water at Reading, the University of Reading Institute, and leads a wide program of research on the theoretical and practical development of early warning systems for natural hazards, particularly for floods, but also droughts and heat waves. So topics that in our region also have become more and more important, as we all know. Hannah advises government and forecasting authorities, as well as humanitarian agencies on national and international flooding incidents. And she was in 2019 appointed Officer of the Order of the British Empire and has also earned numerous other awards. Importantly, she's a fellow of the European Centre for Medium Range Weather Forecasts, ECMWF. You all know that this institute also will have premises here in Bonn very soon, where she's researching Earth system modeling, land surface processes, and flood forecasting. Hannah, thank you very much for making time. I know you have a busy schedule. We're very much looking forward to your talk. After your talk, I will hand over to my colleague Jürgen Kusche, professor at the Institute for Geodesy and Geoinformation, who will lead the question and answer as he's much more into your field than I am. Thanks very much. Looking forward to your talk.
Thank you very much. So hello, everyone. It is lovely to be here this morning. Let's see, okay, there we are. So I study, and some people might say that I'm actually slightly obsessed with rivers and floods and other natural hazards. So today I'm going to take you on a guided tour of these really dangerous and destructive natural hazards. And the idea is to show you kind of what lies beneath that murky and destructive floodwater, so that you can see how the science is helping people to live with floods in the future. And in particular, I want to tell you about the work I do in partnership with the Copernicus Emergency Management Service for Floods, and that's the Efast, the European Flood Awareness System, and the GLOFAST, the Global Flood Awareness System. And how, when we use these global forecasts from these huge computer models of the Earth system, we can be better prepared for floods. We can take that action to keep people safe. But also, that's not enough on its own. We need to look at the role of imagination in communicating these complex and uncertain forecasts. So I often start with a little bit more information about who I am, because it's not necessarily obvious. I mean, I am a flood forecaster, so I started working with the Efast forecasting system as my first job after my PhD. But since that time, I've done lots of different things, working with lots of different types of modeling systems. But the point of them all is the same. The point is to save lives so that we can take that better preparedness. But more and more, I've moved into the field of science communication, because it is no good just working on giant computer models. You also need to make sure that people understand the risk that they are in, and that is the public, but also government, to understand how you can translate these very, very complex, sometimes future predictions of dangerous events. And I've put this lovely picture up by Kelly Stanford, an artist at the Lab Artist on Twitter. You can look her up, she's awesome. She's also taking commissions if you fancy having your portrait done. Because this is the type of thing that I'm really interested in, different ways of communicating concepts. And you can see what Kelly's done here in my hair. These are the famous climate stripes that show the average global temperature change over the last 100 years, with red being bad, hotter than normal. And in the last few years, you can see that we have a changing climate and we have global warming. I'm also a teacher, so I work as teaching undergraduates, master's students, and here you can see me on a field trip in Somerset. And I do really enjoy teaching too. My job is very, very varied. But again, I think the science communication bit is possibly the most important bit. although I'm sure my colleagues at ECMWF might disagree. So let's start. Just think about what flooding means to you right now. What do you imagine? What's conjured up in your mind when I'm talking about floods? Now, bearing in mind where most of you are, I'm sure that you've got some specific images in your mind. This tends to be what people say when I ask them about this. Perhaps it's images that they've seen on the news. It's housing estates covered in water, sun glinting off flooded fields, people being rescued from their houses by volunteers in boats and helicopters, bridges collapsing, or perhaps you have been flooded yourself, or your friends and your family were affected by the floods last summer, and you understand how it feels, for your home to be invaded by this thick, mucky water or destroyed, the psychological trauma that's caused when homes are flooded or damaged by floods, is great, let alone the difficulties dealing with injury and death. Some people take years to get over being flooded, and if at all, sometimes they don't get over that at all, even after they've dried their houses out, and they suffer from post-traumatic stress every time it rains. So wherever you are right now, I don't know whether you're in the home or if you're in your office, but maybe you can just have a look around, at the room you're in, and think about what would happen if everything in that room was destroyed. Maybe your family photo albums, priceless memories completely trashed. And for me, this is an example I use a lot because this is my, it's like a music box that my grandmother gave me. It's got like a little old ballerina in it and lots of precious things from when I was a kid. And it always reminds me of my grandma, and I love my grandma a lot. And I always think, what would I feel if that music box was floating away across the study? It's not just an object, it's my entire life that's bound up in those objects of my home. So I want to talk to you about, what is underneath those muddy, destructive waters. It's not just about the physics and the science, it's also about the people and those things that are dear to them. So we're going to take a little whiz around the world, and I'm going to take you to Mozambique first, where we're going to talk about the twin terrors of these two tropical cyclones that hit a couple of years back in 2019 and caused massive floods just a few weeks apart. We're also going to stay in Germany, and this is the most ridiculous photo I found of the German floods. I never, ever talk to any journalist who's standing in floodwaters because it is the most stupid thing you can do. You put yourself at risk and everyone else at risk because nobody knows what's under those floodwaters. And journalists do this all the time. It was a really, really terrible flood. And, people tend to make it worse often just for the glitz and glamour of it. But I want to show you a little bit of what's behind the scenes of the science in how we forecast flooding, how we're learning about this science every day, from the physics of the very, very tiny and learning about how those individual water molecules interact with each other and the world around them. But also thinking about the physics of the massive. So thinking about huge river basins, oceans, and how when you put all of those into these very fast supercomputers, that are doing all the billions of calculations every second, then they're predicting how all of these things interact at that very small scale to that very, very large scale. But even when we've got these supercomputers and all this very cool physics, it is very hard to predict floods. So I'm going to show you how, when we use kind of the Earth system modeling approach, we can predict floods days or even weeks ahead before the rain's even begun. That's really important. Even before a storm has formed, we can do that. And tell you a little bit about some of the people who are using this information to take early action to save lives and protect communities. First of all, how big a problem are floods? People always ask me, is it really getting worse? But the short answer is yes. It's a very big problem. It doesn't matter how you measure it, they are getting worse. For a number of reasons. So when we look at the UN Office for Disaster Risk Reduction, floods accounted for 44% of all disaster events from 2000 to 2019, affecting 1.6 billion people worldwide. And they're deadly. So the June 2013 floods in India led to more than 6,000 deaths. That's a lot of people. And in many places, they're getting worse because of where we choose to live, right? So we're living in the wrong place, or where we have no other choice but to live. So people are in the way, they're put in the way of the floodwaters. We also put more people at risk because of the way that we have changed the landscape. We've built whole cities on the floodplains or at the coast. And we've cut down trees that help to hold the soil in place, or planted the wrong trees. We don't have a dynamic ecosystem. And because, of course, humans have changed the climate, we've got more heat and energy in the oceans and the atmosphere, and that's making the extremes of weather more extreme than we're used to. And climate change is causing more extreme weather patterns, such as heavier, more intense rainfall, longer rain events that last days or weeks, all these series of rainstorms coming one after another, clustering closer together. And I think in the past, scientists like me have hesitated to say that climate change causes a particular flood to happen, because rivers and land have always flooded since before humans existed. But we can now say with increasing certainty that you can see these human fingerprints in the form of climate change and its impacts on our planet, or many of the floods around the world. So what's really, really clear is we must be better prepared for these more intense and more frequent flood events in the future. And what we also know is that floods hit people living in displaced and poorer communities much harder. And this is what happened in Mozambique. So first of all, let's visit Mozambique. I'm sure most of you know, Mozambique is this fairly big country just north of South Africa. It's got a population of about 30 million people. But what's really key is most of those people live in extreme poverty. In technical terms, so UNICEF say that more than half of the population live on less than 50 cents a day. And that number includes more children than adults. The Human Development Index evaluates life expectancy, access to education, gross national income, and Mozambique ranks 181 out of 189 countries. 70% of the total population lives in poverty. A huge number of children are suffering from chronic malnutrition, and the effects of that really just can't be reversed. Most of the population live along the coast and in the fertile river valleys. So that means that when floods do occur, then much of the population is in the way of the floodwaters. Mozambique's no stranger to floods. Large floods occur on average every 2 to 3 years. And Mozambique is Africa's third most dangerous country in terms of its exposure to weather-related hazards. The coast of Mozambique is regularly battered by tropical cyclones. I'm sure many of you know what these are, but just in case you don't, in the northern hemisphere here around the Atlantic, tropical cyclones are better known as hurricanes. That's what they call when they hit America. But in Africa, they're just called cyclones. They're essentially the same thing. They're these very powerful storms, hundreds of kilometers across. They cause strong winds, storm surge from the sea, and heavy rains that lead to flooding. And the warm waters of the Indian Ocean here are fueling these storms, and the water droplets are continuously evaporating and building up these clouds and the structure of the storm. And you might remember back in the year 2000, there were huge floods caused by Cyclone Helene, and then just a few days later, Cyclone Gloria. And rivers that you may have heard of, such as the Limpopo, the Maputo, the Buzi, the Save, saw record levels of flooding, absolutely devastating large parts of southern and central Mozambique. There were more than 5 million people displaced and affected by the flooding here. And the Limpopo River is already one of Africa's biggest rivers. It swelled and reached up to 20 kilometers across in some sections. So let's fast forward to 2019. So it was 3 years ago in March, Cyclone Idai hit Mozambique, and it hit it twice. And this is unusual in itself because of the way that the storm tracked from the ocean over the land before going back out to sea again and then coming back in as a monster. So it's on its first visit over land. It was a fairly weak storm, but it still brought enough rainfall to cause flooding in Mozambique and Malawi. And then the second time it came round, it was this strong tropical cyclone. It had winds and rains, and it caused huge damage and affected more than 3 million people. And then, you know, when the country was just about cleaning up, and it was just 6 weeks later, I think, another intense tropical cyclone, Cyclone Kenneth, slammed into northern Mozambique. And this was the strongest cyclone to hit Mozambique in modern history. So let's take our tour right into the heart of this monster. What's being in the middle of a tropical cyclone really like? Well, you know, usually the first thing that comes to mind when we hear about hurricanes or tropical cyclones, what we imagine is the destructive winds. So you tend to think about the dramatic pictures you see on the news with like these characteristic swirling clouds, but like palm trees bending over and debris from buildings being thrown about. And yes, the noise and the sight of the wind is pretty dramatic. However, in many cases, the water can be much more dangerous, both for people and for property. So coastal areas can be extremely vulnerable to the waves whipped up by the wind, the storm surges that are coming in, and this extremely low air pressure in the center of the storm can cause these sea levels to rise several meters above where they would normally be. And if you're further inland, you know, we've got many people living here beside the rivers and in these valleys. People are vulnerable from this heavy rainfall, but also from flash floods, from landslides, and then the rivers just expanding out over their floodplains for weeks. The impact of the rainfall and the floods are the longest lasting. So long after this storm has blown away and the wind has died down, it's still flooding. And what makes it especially bad is that severe flooding cuts off communities from the outside world. It prevents people from getting into the worst affected areas with the help that they're trying to bring. And often humanitarian aid agencies are desperately trying to help during the weeks and the months after a cyclone, but they just can't access the people and the areas that need it because the roads are underwater and the bridges have been washed away. And you need a helicopter to get anywhere. And not many people have got helicopters in Mozambique. So it's therefore really essential for humanitarian and civil protection agencies to have the right information on the upcoming rainfall and flood risks, so they can get people out of harm's way before the storm hits and even deliver aid to places that will need it in a few weeks' time. This is the European Commission's Emergency Response Coordination Centre's daily map for tropical cyclone Idai. And you can see the huge rainfall accumulations here. That's the very blue bits. And we can trace Idai as a tropical depression as it swings round, follow the yellow line here. So it swings around and it intensifies over the Mozambique Channel, and then loops back, and then it slams into Beira again. And that Beira is a port city. It's got about 500,000 people in it. And down the bottom, you can see the really high storm surge. Possibly it was even higher than that. So it got up to possibly 6 meters in some places. You know, that's as tall as a giraffe, like coming at you from the coast. On the right here, we've got the red flooded area located by satellite. So you can just see how very widespread the flooding was. As a tropical cyclone makes landfall, the surface friction increases at the front edge of the storm as it moves from this relatively flat sea to the lumpy, rough land. And this in turn pushes more of the air into the eye wall, into that central column at the heart of the storm, and increases the vertical motion of the air occurring there. And this is important because it sucks up huge amounts of moisture-laden air, which falls out as rain. So this is what's responsible for these torrential rains that are associated with tropical cyclones. After landfall, Cyclone Idai quickly weakened, but it continued to move slowly inland, resulting in this continuous rainfall for several days that led to the widespread and devastating flooding. As is often the case for such floods, we have no idea how bad the floods got because no one was able to take any measurements in such conditions. Any of the automatic machines which are designed to measure river levels were completely overwhelmed or destroyed. But we do know that rivers levels went up extremely high, extremely fast in the days following the landfall, and the water stayed there for a very long time, taking weeks to go back down again. And this is just one of the difficulties of doing science in a disaster zone. And even worse for the flood experts in the area, the Met Office, the meteorological office in Beira, was completely destroyed by the storm and the floods, along with decades of precious data, which have been painstakingly assembled by hand and stored in these handwritten notes for decades. So all of those valuable local climate records are now lost forever. So the seasonal wetlands here, they just turned into these inland oceans full of muddy floodwater. And then we had Kenneth come along less than 6 weeks later, just as the recovery was beginning. And the system intensified into a tropical storm, at which point it got its name, Kenneth. And Kenneth continued to rapidly intensify and was declared as an intense tropical cyclone with maximum 10-minute sustained wind speeds of 215 kilometers an hour at one point, which is insane. It weakened slightly and made landfall on the evening of the 25th of April in northern Mozambique near Pemba. This was a really strong tropical cyclone, and the result was severe flooding again, particularly across the Cabo Delgado province of northern Mozambique. So we had, deaths from this, destruction of at least 2,500 homes, but also the loss of crops, fishing boats, equipment. So people's livelihoods were completely destroyed by this storm. So let's meet some of the people who were at the heart of this. The Mozambique Red Cross was already working on development projects in the area before the cyclone hit. And because they were there, the volunteers were able to warn people in the communities to take cover or move to higher ground. And then when the cyclone did hit, they were able to evacuate people and provide immediate help to the communities. This here on the right on this picture is Janio Dambo. He works for the Mozambique Red Cross, and he's one of our research partners in Mozambique. And he was kind enough to give me these photos of the flooded communities in the aftermath of the cyclones. Here you can see Janio in Beira, standing in the floodwaters caused by Cyclone Idai, talking to the community. And here you can see Janio and Red Cross volunteers unloading a consignment of blankets, mosquito nets, tarpaulins outside the Red Cross office for Sofala province. And on the wall there, you can see the very recognizable logo of the Mozambique Red Cross. And much of the time, the Red Cross's work in Mozambique is spent with rural communities, helping health programs, dealing with COVID, immunizations. When you're in a country when you've got this really hazardous weather, it's combining with such poverty. They just spend so much of their time just responding to these human disasters, to follow the storms like this. You can see here in this photo here, you can see Janio is wearing a German Red Cross t-shirt. And this is because the German Red Cross are supporting the Mozambique Red Cross in setting up something called forecast-based financing. And that idea means that instead of waiting for a disaster and then asking donors to give some money to help in rescue and recovery, you can release that money before something bad happens by using forecasts of tropical cyclones and floods and other hazards, and then look at the forecast to see if something bad is going to happen. And then, so that money can be used to make preparations in advance. The Red Cross were in no doubt about the seriousness of the crisis with Idai, and they said, this is the worst humanitarian crisis in Mozambique's recent history. It's humanitarian catastrophe for the people of central Mozambique. Large parts of Beira have been damaged. Entire villages and towns have been completely flooded. Rescuers are scrambling to pull people trapped on rooftops and trees to safety, and many, many families have lost everything. Flooding is truly monstrous. So that is absolutely true. And this is, one of the things that drives what I do. It's just to see the destruction and the harm that they caused. So let's jump from Kenneth a little closer to my home. This is the River Kenneth. And that's just down the road from where I am in Reading. I'm sure many of you, like me, have found the shift to online life rather tricky. So my favorite antidote to the hours and hours of back-to-back online Zoom meetings is to take a walk or a run sometimes, if I'm feeling brave, over to the river and to follow the swirling song of the River Thames. I find rivers utterly beautiful. I always have since I was a little girl. I grew up in London, but most of our holidays were to the south coast of the UK, to a place called Devon, where my grandparents lived. And I spent many a happy week swimming in the moorland rivers and collecting pebbles and digging and diverting these intricate channels on sandy beaches. So this photo is the mouth of the River Kenneth, where it meets the River Thames in Reading. And the Thames is flowing from left to right towards London in the picture. And the Kenneth is flowing from the foreground into the River Thames here. And I do literally, like I really do this. I just stand here on this spot, mesmerized by the water, because I love the way that you can see the waters of the two rivers meeting and running along side by side. And the way that the water tumbles over itself in these ropes, and you can see the eddies spinning and circling, and you know the sunlight dances on the surface, and you can see the upwellings of the water. They look a bit like hippos sometimes, but they always look really unique. And I find this is like a display of nature, just for me, you know, repeated, never again, just especially for Hannah. And then if we jump kind of to the other side of the world again, and travel to South America, we can see the beauty of rivers in a much larger scale. This is the River Amazon. This is the image that I've got permanently on the background of my computer screen, and I stare at it all day. I'm staring at it now, in fact. Sometimes when I'm in dull committee meetings, I'm often just looking at this picture. But look at the way that the river loops and meanders and threads. It's pushed into these really extraordinary shapes by these conflicting forces of physics and chemistry and biology. And I find this image a bit like a puzzle, because, you know, the closer you look, the more tributaries you can see, these tiny meandering baby rivers. And this is a huge river. This is the Amazon. So rivers are beautiful in both their simplicity and their complexity, and the swirling and the threading and the chaos of the river flow is just beautiful. And it's this complexity that also intrigues me, because it's essential to be able to work out how rivers flow and to predict when a flood is coming, because as we've seen from Mozambique, and as I'm sure you also know, rivers are beautiful, but they are beautiful monsters, and they have these split personalities. They draw people in to live beside them when they are peaceful, provide food and transport, but they quickly change character and they destroy everything around them. So what we really want is the power to be able to benefit from rivers when they're good, but also to know in advance before they go bad, with enough advance warning to take action to protect the people and the communities. So that is the aim of flood prediction, but it is a really, really hard job. So why are floods so difficult to predict? So the weather predictions have come a long way in recent years. And today's 3-day forecast is as accurate as a 1-day forecast was in the 1990s. But as we all know, they're never perfect. Rainfall is one of the hardest parts of the weather forecast to get right. And these days forecasters are pretty good at getting the temperature or the wind speed right. But on many occasions, we still struggle to predict exactly how hard the rain is going to be, exactly where it's going to fall. And that's because we have to be able to predict a lot of different complicated underlying conditions to make it rain. The temperature of the air, the humidity, the direction of the wind, where the clouds are, what type they are, how big they are, you know, and even then forecasters can still get it wrong. And if you multiply all of that uncertainty within the weather forecast with the complexity of modeling exactly where the water's going to go when it hits the ground, how it travels through the landscape, both on the surface, you know, and under the ground, then you start to get an idea of the difficulties that we as flood forecasters face. So in effect, we have to take account all of the possible different routes through the landscape that a single raindrop might take. And there are billions upon billions of different possibilities. So if we want to stand a chance of knowing what will happen in the future, this requires a lot of assumptions about what will happen now. So when I stand at the mouth of the Kenneth, watching the water flow, I think about all the many, many droplets of water that are passing by me right now. So where did each one of them come from? Which pathway through the landscape did they take? When did each one fall as a drop of rain? And it can seem like an impossible task to try and understand this, the flow of the river. So sometimes I put on my superpowers and pretend I'm a superhero and pretend that I can see every single droplet here. And I imagine that I can see each droplet really clearly there's an individual blue pebble. So I don't know if you can see this on the screen here. I might be very small. It's like a glass pebble. So in my mind, when I look at the river, I can see it's full of these tiny little blue pebbles. And each one of those has its own history, so where it's been, and its destiny, where it's going to. And I imagine that I can see them all and read them all and follow them all. And it's like a journey through time. So if we just kind of slow time down and stop and freeze it, and then we zoom in until we can see each one of these individual drops of water. Think about each one being maybe a different size, made up of a different number of molecules, different history. Then we can rewind time and follow each one back to its source. So if you think about all the different ones that you might come across, perhaps this droplet fell in some really heavy rain yesterday. It's always raining in Reading. Perhaps it fell yesterday in the street just over there and has rushed straight over the land to the river. And perhaps this one fell in some rain at the weekend in the hills, right at the headwaters of the river catchment, and has been working its way through the tiny brooks, the streams, and then the bigger rivers. And perhaps this one fell 2 years ago, just as our life was being locked down for the first time, and has been pushed out into the river in the latest rainstorm. And perhaps this one fell in a summer rainstorm in the 1970s and percolated down to the groundwater, where it's moved through the rock to be finally discharged into the river. And I always try and imagine which drops were the rain that fell on the day that I was born. So my challenge to you is the next time you go and look at a river, take a moment to stop and go beyond that mass of swirling water before you and zoom in and look for these little blue pebbles and ask yourself, where did they all come from? When did they all come from? Because this is all part of an Earth system cycle. And these blue pebbles of water have been around several times, being evaporated up from the land and the sea, transported by the wind and rained down on the land again and again. And it seems incredible, but this trying to recreate this system in a computer model allows us to forecast floods, because we can use the idea of the Earth, this giant natural system, to trace these billions and billions of pathways of water and predict when they go across the land, when they're going through the soil to reach rivers, and ultimately when they go downriver to where people live and work. And this is a representation of the ECMWF Earth System model, the European Weather Centre. So if we now nip across to the European Centre and we look, we imagine all of those fast and powerful supercomputers working away upon the billions upon billions of individual options, assembling a picture of what the Earth system looks like now, in a day from now, in a week from now. And the European Centre for Medium Range Weather Forecast, or ECMWF, was founded in 1975, and it's this independent intergovernmental organisation. And as we already now know, it's now based in 3 locations, here in Reading, there in Bonn, and also in Bologna. The computers are in Bologna. And I'm lucky enough to be an ECMWF fellow, and that allows me to collaborate closely with some of the leading experts in meteorology from around the world. So I work in a large team developing the Copernicus Emergency Management Service for Floods. And in March 2019, I was part of a team of forecasters putting this Earth system way of flood forecasting to the test. And we analysed the tropical cyclone track forecasts. We looked at where and when the cyclone might make landfall, but also where it might be dumping all of that rainfall that it was bringing with it. Several days ahead, the tropical cyclone track forecast indicated that both of these cyclones, Idai and Kenneth, were problematic. And the Global Flood Awareness System, the GLOFAS, indicated severe flood events. So we provided emergency reports to the UK government and humanitarian partners, including the Mozambique Red Cross, to detail the upcoming flood risk. So this crucial information is where would the cyclone move next, how much rain is expected, which rivers are likely to flood and when would the flood water recede, really important, and what areas are likely to be inundated by the flooding and how many people were at risk. The Red Cross and the UK government told us this was the first time that this flood risk information had been provided in real time, and it was extremely valuable in helping to plan their aid efforts. So it was great. The aid agency used our reports. We think they sent assessment teams to the correct areas, moved aid and equipment to the places they would be needed the most. And we talking to Janio from the Red Cross, you know, he said they gave out chlorine so people could purify their water, and they could use supplies already stored in Mozambique to help people, including shelter kits, tarpaulins, blankets, sleeping mats. And this is all really encouraging, and perhaps we as hydrologists and forecasters can make a difference. However, forecasts and early warnings are not useful in a vacuum, because it is absolutely no use having massive computer models predicting what is going to happen if people do not know what to do in a flood, and they cannot imagine the danger they are in. So as I said, I work with the Copernicus Emergency Management Service for floods. It provides early warning information across Europe with the Efast and across the world with the GLOFAS. It provides this early information to national and local authorities, so not the public. And it has an interface, and you can go and have a look yourself and have a little look about what the Efast system is about. There's lots of information on the web. So as I said, after my PhD, I helped to set up the Efast, and that was following these devastating floods in Europe in August 2002, with the idea that it would never happen again, that there would never be this type of destruction in Europe ever again. And now I work closely with the Efast and GLOFAS teams, and I'm an independent flood scientist, so we have a research group at Reading, and we are the research wing, I suppose, but we don't work for Efast and GLOFAS, we are researchers. I'm mostly interested in, you know, improving the models in every single way that I can. So all the way from developing new components for the Earth system, working on snowmelt routines, all the way through to working with the people who need those forecasts and warnings, and how you can interpret them and actually improve the communication to understand the risk. Efast has been around a while, it's been operating for a while. There were some very severe floods in the Balkans in May 2014. And I was looking at these forecasts, really, really high levels of flooding, and Efast was involved in providing information 8 days before the flooding to the European coordination centres and also local authorities. So what happened in the Germany floods? I'll take you on a little tour of my perspective of what happened. So I wake up in the morning and I look at Efast and GLOFAS. It's always flooding somewhere in the world. It really, really is. And over the weekend, so probably on Saturday, I was looking at the system thinking, oh, you know, that looks pretty bad actually. And certainly there was a high probability of flooding for the Rhine later in the week. And as the forecast, you know, as you get closer to a flood event, the forecasts get more certain. So, you know, in a few days' time after this, there's no doubt that there was a major flood coming. And Efast sends these bulletins of information by email, and that was sent to the relevant national authorities on the Saturday, July the 10th. And more updates were continuing over the following day because you get more precise predictions as you get closer to a flood event. And formal flood notifications were issued to authorities in Germany, Belgium, the Netherlands, Switzerland, Luxembourg, the Emergency Response Coordination Centre of the European Commission throughout Monday and Tuesday. And again, as we get closer to the event, the uncertainty in the forecast shrank, and the predicted start of the flooding was pushed to Wednesday for the smaller rivers and Thursday for the larger downstream rivers. So what's the kind of thing that I'm looking at? So when you go onto the Efast system and you could see these floods were coming, I could see them because like there's lots of red everywhere, kind of shouting at me saying, oh, you know, there's a serious event coming here. And the point of this system is to give this early heads up, you know, be aware something is going to happen here, to allow the time for national authorities to run their own systems, to make sure they've got the local information in place, you know, to make sure that nothing is missed, so that you have that early indication of flooding is happening. And there are two parts to the system. There's like the river bit, and then there's the flash flood bit. Now, I learned recently that there's no word in German for flash flooding, which is interesting. So what I mean is really, really heavy rainfall that causes rapid flood to happen really fast. And in the mountains, that tends to be the river channels tend to have like a wall of water coming through. But also in the cities, you can get flash floods just from really, really heavy rainfall. And we saw some devastating scenes in the summer in China where those types of floods had happened. So I remember waking up and looking at the news and thinking, this is terrible. You know, this is a really, really bad event here. There's something has gone wrong here, because I'm sitting in Reading and I could see that something really big was happening. And this is Germany, you know, this is not Mozambique. This is a place where there are forecasting and warning systems available. You know, people should not be living in very dangerous areas. And yet so very many people have died. And then I'm very interested in science communication, which means I do a lot of work with the media, but not just me. The entire team at Water at Reading are very interested in communicating, you know, how floods happen, why they happen, and like talking about things as expert hydrologists. So the entire team in Reading were basically mobilized to try and talk about this event, as we do for many other flood events all the way around the world. You can see just here, this is our group photo this year. We had to get, we got this artist in to draw our group photo because of course we're all still working from home. And I also wrote this piece for The Conversation, which again is about trying to put the facts of the case out to the more general public about how floods work and what might have gone wrong in this case. Now, Efast provides, you know, a probabilistic forecast, an ensemble of possibilities. And you can think about that in this way of like, what's kind of a worst case scenario? What's the most serious thing that might happen here? And what's the most likely thing to happen? But it's really important to look at this worst case scenario for planning. So you understand what the possibilities might be, what actually might happen. You know, is that an acceptable risk? What can you do to prepare for that type of risk? And I think that is one of the things that went wrong for the Germany floods, is that nobody was really taking notice that this scenario might actually happen, even though we had some evidence that it might. So this is the other part of Efast. This is the flash flood layer. And just to show you what it looked like, so purple means bad, okay? Purple is bad. That's the highest level for flash flood risk in these valleys. And you know, this is quite tricky to do, to predict exactly when and where that flood might be. But certainly in all of these locations, you had an indication that there was a very strong chance of a flash flood occurring. So, you know, tragically, the whole system here that is designed to save lives by ensuring people act on warnings before floods arrive did not work as it should have done. And it might be that individual parts of the system worked exactly as they were designed to do. And it's certainly true that some of the forecasts were accurate and there were some warnings issued through the official channels. This is the kind of the system chain I'm talking about here, just to put that into a picture here. We've got observations, weather forecasts, forecasts of the hazard, what the actual impacts on the ground might be, like people's houses destroyed. Then like a siren, a warning, any kind of information to the public, and then decisions taken by, you know, municipal authorities and individuals who are being asked to evacuate. And in some areas, many authorities did act in time to evacuate people and erect temporary defences, move vehicles to higher ground, but it didn't happen everywhere. So what I got very, very angry about is actually people were insisting that the warnings were adequate and that the agencies did their work well. But that's nuts, because claiming, you know, the maiden voyage of the Titanic was a success because 99% of its engineering worked perfect throughout, is just, that doesn't make any sense whatsoever. You have to admit that the system ultimately failed in order to learn lessons so people are not at risk in the future. So science is in a large part is about helping people see the invisible. And what is the use of a perfect forecast if the people it's supposed to warn can't see the danger that they are in? What's the point in using a giant computer model to predict what's going to happen if people don't know what to do in a flood? Municipal authorities couldn't imagine that such dire forecasts might be correct. The scientists couldn't imagine that their forecasts, which were delivered in reasonably good time with accuracy, could be ignored. Many of the people living in harm's way just couldn't imagine what a 9-meter wall of water would do and how badly they would be affected. And the best scientists use their human abilities, imagination, creativity, collaboration, communication, empathy, to make discoveries and reach new insights. But when it comes to telling people about them, you know, we turn into these robots. We're unable to deliver these important messages. And if people can't visualize the threat of a river ripping down their street or a lake appearing in their house, then people will die. So these elements of flood warnings must improve. And my last point is about memory as well, because memory comes into this as well. To really understand the risk of flooding, we need to look much longer than a human lifespan. And this was certainly the case in Germany. It had flooded here before and people had forgotten. And they just, you know, did not imagine they were at risk because they didn't have that collective memory. And that's where flood forecasting models can come into play, because they can bring you that memory, but you have to believe them. So certainly one of the biggest things that I think we need to address, not only in improving our Earth system models with the best physics, is that we need to address our imagination problem, because I think that lives depend on it. I'm just going to finish here with the warming stripes, the climate stripes for North Rhine-Westphalia from 1881 to 2020. So you can see this is an ever-growing problem and things are going to get worse. Thank you very much.
Thank you very much, Anna, for your great presentation. I think you raised a couple of extremely important points, and I'm sure there will be questions now from the audience. So please raise your hands, or just switch on your camera if you like. Maybe I should make a start, yeah, so people can get warm up. So you mentioned the power of these of system models, and I mean, to create a flood, it needs precipitation and it needs certain soil conditions. And I think the Earth system models, and particularly what's run at the ECMWF, is good at predicting, forecasting precipitation, but maybe it's not that good at predicting the actual soil conditions. So where do you think is the uncertainty, and what should we do about that?
Yeah, actually, absolutely true. So when I first started working with ECMWF, it was much worse. So it's getting better, right? And some of that is about thinking about soil layers, you know, how you tile it, how you represent. So soil hydrology is really difficult to represent even in catchment models. When we just take a catchment of a small river and try and discretize it, put it into a grid, the physics of like the flow through the soil, you know, it makes sense in a lab, but when you go out and try and model a catchment, the uncertainties are too great. So the physics doesn't make sense anymore. So we have this interesting point where actually going to a less physical representation of the soil can actually improve some of the flow forecasts that you get in rivers. So we've been experimenting with some of these types of techniques, looking at how you could change the soil representation in the land surface model, or sometimes you want to actually just rerun some of the catchment hydrology as a post-processing of what's happening in order to then create the flow. My desire is to see all of these things done within the Earth system model, but they are very difficult to experiment with because they are huge, and you can't run 10,000 simulations to test the uncertainty. Otherwise I get told off for using all the supercomputer power. So it's a bit of both. Certainly that we have made improvements into that soil representation. What we do know is if you can assess where you're confident in your soil moisture predictions, you know where you're expecting the model to do a good job and where actually it's not going to do a good job. So you have to interpret the forecast slightly differently in those areas where you know it's not representing that soil hydrology very well.
And that probably makes it even more difficult to communicate a probabilistic forecast to people.
Definitely.
We have questions now, and I think Daniel was first. Daniel.
Yeah, thanks. Thanks, Hannah, for this very, very nice presentation. I'd like to ask perhaps a little bit of a provocative question. So these pictures that you showed from Efast, they're actually quite interesting, and especially the flash flood forecast. That's actually quite interesting to explore in detail, which I've been doing the past few minutes. My question is, since you've highlighted, let's say, the connection that we should really try to enhance between the quality of our forecasts and the way that we communicate them both to, I guess, stakeholders and the general public. When one looks at these forecasts and looks at the legend, you know, what it reads is that the purple is an extreme flash flood severity with more than 20 years return period severity. And I was wondering if you could comment, you know, this is a thing that we tell the general public means nothing.
Right.
As you said, right? No one remembers what happened 20 years ago, if you were there at all. And in my opinion, what we lack, of course, is some kind of horrifying quantitative impression of the severity. That is, you know, as you said, 9 meters of water moving at 5 meters per second. But these type of forecasts that are available here do not produce these quantitative results. So I wanted to kind of pick your brain and be provocative about what the outlook is from your point of view.
Yeah, it's really important to note that I absolutely agree with you. So to put this in context, the Efast has some problems because it is designed to support national authorities and it is not designed to be public facing. And as soon as it starts doing impact-based forecasts, which is what you're talking about, explaining what might happen on the ground, that is treading on the toes of the national authorities because it's their statutory responsibility to do that interpretation. So Efast really struggles in its communication because there are boundaries put there about how it can communicate. Now, I hate return periods. They are a stupid way of trying to communicate anything, and even hydrologists can't understand them half of the time. But they are put there for that specific reason. Now, in the UK, in England, we have a broker system, a bit like Efast. So the Flood Forecasting Centre is a collaboration between the Met Office and the Environment Agency who run the flood forecasting. And what they do is they broker this information into impact-based forecasts. So they have this matrix, and recently we saw it goes amber if, you know, there's a severe likelihood of a medium flood, or goes red if there's a high likelihood of a big flood. So it's colored in terms of a traffic light system, and it tells members of the public and it tells the local forecasting authority what might happen on the ground. So there was a severe danger to life warnings out, and it said, you know, people will be washed away, numbers of properties will be flooded, infrastructure will be affected. So electricity grids were affected, train lines were affected. So it's translated that purple 20-year return period into, you know, what actually might happen on the ground. But there's a stage further, really, which is what should you do in that circumstance? You know, if I'm just sitting at home in my house with my family, what am I supposed to do at that point? So there's a whole nother layer of preparing so people understand what action they need to take once they've received these impact-based warnings. So I totally agree. And it's interesting working on lots of different flood forecasting systems because they have different, it's always the politics that harms the communication of the actual forecast itself because of where it sits within the framework of these national authorities.
Thank you. Alicia?
Thank you very much. Thank you, Hannah, for this very thought-provoking presentation. As you rightly highlighted, early warning of floods is very important to save lives. But we also saw that sometimes some authorities do not fully listen to these forecasts. And in some cases, for example, even if they do so, in the context of, for example, low-income countries, perhaps there is very little they can do. Of course, that would save lives, but in terms of infrastructure damage, other things. So I was wondering how we can make this foolproof, even if someone doesn't listen to that much, so that how we can reduce this damage from floods by reducing vulnerabilities, reducing all the exposure through land use change or through some engineering solutions. I was wondering, I saw in your slides you pointed about the economic benefits from early warning. Is there any modeling done showing different options of early warning action? So proactive actions to reduce any kind of impacts of flooding, and how that is, what are the key areas that you see are the remaining gaps in that sort of modeling? Thank you.
That's a really, really good question. So I work advising the Environment Agency in England just on these things, because what they do is they run lots of scenarios for 25 years, looking at the different options that you could do in flood preparedness. You could think about things like building large structures. So everyone's talking about the next Thames barrier in London, how we can protect London. And also, around the country, all these hard engineering solutions about planning changes. So stop people maybe living on the floodplain, but that's got a lot of economic consequences for it. Then they have to build on land that's more expensive and all those kinds of things. Natural flood management. So looking at how you use your landscape, work with farmers, store water on floodplains, and then of course early warning and getting people out of the way. And it is a mosaic, so you need all of these things in order to keep people safe. You also need people to understand what's going on. So there's a whole load of education starting at school age, in people understanding what to do to keep themselves safe. So when you look at all of these different options, early warning and forecasting is only a part of it. Definitely, you must look at the other things. In England, planning is one of the biggest problems that we have. There's a big drive from government to just keep building houses. However we're going to do it, let's just build houses. And that causes, stores up problems for later down the chain. And if you don't assess the economic impact of that future risk, then you are doing a disservice, I suppose, in the long run. But of course, government cycles don't work on the same cycles that floods work on. So it is very complicated. When you're looking at somewhere like Mozambique, no doubt anything that you can do within that sphere to reduce vulnerability, to simple diversification of income as well. So you're not relying on just one source of income. So if you are affected by a tropical cyclone or a flood, then you can do something else while you work to recover from that flooding. Now that's a reasonably straightforward principle, but of course it's very difficult to implement in practice. And we're working with people around the world. So in Bangladesh, they're also looking at this type of, that's a completely different thing from forecasting and warning, but it's just as important to make sure that people can recover very fast from a flood.
Abdul Rashid.
Hello.
Hi.
Thank you. I have two questions. So I'm a development economist and I'm doing my PhD here. And one of my projects will look at, there was extreme flooding in Nigeria in 2020. And it was like once in 100 years kind of flood. So I want to use that as my source of exogenous shock. So the first question is there a resource where we can find this weather attribution of these floodings for African countries? Because I couldn't find for Nigeria. And second is the Nigeria Hydrological Services Agency provides forecast at municipal level. So some municipals are highly probable, some probable. But what I want to use is to find municipalities that are highly probable, but some of them were flooded, some of them were not flooded. And I will use that to do some household surveys and lab in the field experiments to see that, to make the assumption that since these are in the same category of being flooded, but some were flooded and some were not, we can assume the population is similar, and whatever difference we find, we can make it as a causal impact of the floods. So is this something reasonable from forecasting background? Because for economists, we may think, yeah, this could be, these are like exactly similar communities. So I want to hear your view on that.
Okay, those are two very different questions. So I'll do the first one quickly. I don't know of any attribution data set, but certainly you can look on the Efast system and you can go back in time and look at previous forecasts. So you can get some information on what floods were probably happening at that point. And also, of course, ECMWF and Copernicus have some information on past weather events as well. So you can look up what the weather was actually like during that time and get some indication of rainfall and things like that. Your second question is very interesting, and I'm always interested in these types of trying to draw out information, you know, with comparing communities. It is really hard, and a really key thing is the people who you're talking to, have they been flooded before? Because that's a really key difference in people's behavior when they're flooded again or when they're not flooded again. And so that history of exposure to floods and the underlying kind of, like I was saying, the trauma associated with previous floods, or actually any other trauma that's happened to them before, can really change their response in terms of what you might find in those types of surveys. And certainly working, so we have social scientists as well in our water team who are going out and working with flooded communities to really explore this issue about how, as a forecasting agency, the Environment Agency kind of just hand back all the responsibility to those communities and say, you're going to get flooded, you know, go sort yourself out. And of course, the flood communities are like, well, what am I supposed to do now? And then you just worry all the time. It rains, you know. So those are the kinds of things that we've been exploring at Reading. But certainly trying to look for, can you see any statistical differences or those kinds of things are really, really hard without actually doing some interviews. So I don't know if you're able to do interviewing as well, but I would always recommend doing some kind of community interviews alongside a survey, because I think that actually it draws on a different type of information, so you can triangulate really what you're finding in those times of surveys. So good luck.
Thanks. I can see Jan.
Yeah, thanks, Hannah. One thing I learned last year on an excursion with the Swiss Center of Avalanche Research, so the frozen droplets that can also do a lot of damage, is that you can actually overdo the accuracy and the intensity of early warning, because it leads to people feeling more secure than they actually are and then behaving in riskier ways. Right. So I'm just wondering, given that this is so complex and we are as scientists always pushing for more accurate models, and so are there any systems or cases where you would say, wow, this is really a system where science is combined with early warning and disaster risk management in a way that could be a model where we could learn from? Apparently the systems we had here didn't do the job, and the other examples you showed were also more examples where the system failed. So are there any
Yeah, yes.
This is for hope.
Does it? Yeah. Well, does it work at all anywhere? Is the question. And I think it does in parts in different places. So we know that earthquake, tsunami warning. So Japan they're pretty hot on that. And I think one of the main reasons that that works so well is because they start when the kids are 3, and everybody grows up knowing that that is a dominant risk in these areas. And then that's a different type of approach to things. And floods, of course, might not affect you for your entire lifetime, depending on where you live. And then suddenly they might become a risk. So it's a bit of a different type of risk, because floods kind of move around like some kind of, I don't know, mob in Minecraft. You know, you can't control them. So what does work here in the UK? So we had some floods a couple of weeks ago, and the temporary barriers went up and they were again overtopped. So the people behind them, this has happened before, you know, there's this feeling of safety. Oh, the warnings have gone out, the barriers have gone up, we're going to be fine. But actually the communication between the Environment Agency, community teams, and those people living at that risk was so much better this time that then they realized that the barriers were only going to do it up to this point, and then they would need to evacuate. So they understood the residual risk to themselves and their property much better. I'm not saying that we get everything right in the UK. I'm not saying that, and we will keep working on it. But that communication and trust, the trust between those people working, and that's been built up over the last 10 years, really, when we had a really bad problem here in the UK, because there was no trust in the Environment Agency whatsoever. And there were some very bad floods, and the opinion was the Environment Agency do not know what they are doing. They are unfit for purpose. We should disband them, you know, all that kind of stuff. But that was just poor communication about what you can do and what you can't do, what the residual risk is. So this again comes back to this idea that you can have these fancy models and they can be very accurate, but that's not the biggest part of the problem. The biggest part is learning to talk to communities. And we still don't know enough really about how different communities respond to floods and how they recover, which is why these types of PhD projects are really, really important.
Are there final questions? Daniel, I can see your hand. Is that from the earlier question, or is there a new question? No, it's not. Okay, so maybe I can pose the final question. I'm not a forecaster, but I worked with operational agencies in, Bangladesh, West Africa, but also in Germany. And my feeling is that here in Europe, we have all these wonderful instrumentation. We have a lot of systems in place, and people in the agencies are hesitant to rely on space data, and probably also a little bit on numerical models. Since we have, all these gauging systems along the rivers, everything is so wonderful, which is, of course, not in a country like Bangladesh, where a big flood wipes everything away. And could it be that this creates a false sense of security in our operational agencies?
That's a big question. I don't know, actually. I know the UK situation better, so I'm going to be honest about that. I work very closely with people here, and I think that they don't think that their observational network's very good at all. In fact, they're always complaining about them. We don't have enough rain gauges. Certainly, we don't have enough monitoring stations, and they're all in the wrong place, and they get bypassed when there's a big flood. So we don't actually have any data of big floods. And it was good a couple of weeks ago, because they took the arc boats out. These are the little remote controlled boats that you can put on the top of the river to measure the velocity and get a better understanding of the discharge readings on the river. And it was like this deployment of all this new kit. And it's the first time I think that there's been an investment for a long time in hydrological monitoring in the UK. So I think possibly it's different in Germany. I do get the feeling that things are thought about in a different way, and that sense of security, this can never happen to us. We're a civilized nation. We've got it all right. We've got all the information we need. I did get a bit of a sense of that. But again, I didn't investigate this thoroughly, so I don't want to say something that's not true.
Okay.
But you might, you might be onto something.
Okay, thank you. So I will give back to Jan for probably for the final word.
No, I don't have any major final words. I just wanted to say thanks a lot. I think that was a really illustrative and exciting talk. I've learned really a lot. And I think one or the other might want to follow up. So we have your email address. Expect maybe one or the other contact. Of course, I think much of what we are doing here in the next couple of years and building up here also links to what you have presented. So I think we would be very glad to be able to maintain contact and maybe work together on one or the other topic. That would be great if that were possible. Other than that, thanks once again for your talk.
Thanks for listening.